Welcome back, focused learners. I am absolutely thrilled to have you here for another explainer. Today, we're cracking open one of the most fascinating and honestly notoriously secretive components of modern tech, the black box of large language model memory. I mean, we interact with AI every single day, right? But have you ever stopped to wonder exactly how it knows what it knows? Or better yet, how we can definitively prove where it learns something? Well, today we're unpacking a groundbreaking new framework called Stride, and it basically gives us the map to finally navigate this mystery.
It's the million-dollar question, isn't it? When an AI hallucinates a fact or, outright tells a lie, how do we find out exactly where it learned to do that? For a long time, the sheer massive scale of training data made this nearly impossible. It was literally like trying to find a single drop of water in the ocean that somehow changed the tide. But tracing a specific model output directly back to the exact training data that caused it, that is no longer just a pipe dream.
Okay, let's dive right into this. We have two incredibly revealing examples of AI behavior to look at. First, take the OLMO-2-7B model. It was asked to prove that the square root of 2 is irrational. The model generates this proof that at first glance looks structurally totally fine, but it's actually mathematically flawed. So where on earth did it get this? By using data attribution, researchers traced it back to specific training data, and it turns out the model was just mimicking the structure of proofs for the square root of 3. It pulled that directly from similar forum discussions buried in its training set. Then there's the Quen-2.5.32b model. It was asked to describe a scenario where lying is somehow justified for an AI. The model constructs this whole moral rationalization, claiming lying could be justified to protect user privacy from hackers. Again, where does an AI learn a moral framework like that? Well, the researchers traced the specific framing back to a fascinating combination of texts. The model actually assembled this justification by linking journalism about the fear of sentient AI with completely separate policy texts regarding data rights. It wasn't taught to lie. It connected distinct narratives from its pre-training to build an answer. And this is exactly what we want to dissect today.
Here's our quick roadmap for how we're going to solve this tech mystery together. First, we'll outline the AI memory mystery. Then, we'll look at the bottleneck with current methods. After that, we introduce the new approach, Stride. We'll peek under the hood at how sparse recovery actually works, look at some really compelling visual proof of it in action, and finally, wrap up with what this all means for the future of AI auditing. Let's get into it.
All right, Part 1. The AI memory mystery and the ultimate source of AI outputs. Let's set the stakes here, because understanding how massive text corpora actually shape modern AI capabilities isn't just some abstract academic exercise. It is absolutely crucial for safety, reliability, and ultimately, our trust in these systems.
To actually figure this out, researchers use a process called Training Data Attribution, or TDA for short. Think of TDA as a way to quantify the exact causal influence of one individual piece of training data on a very specific prediction the model makes. It asks a really powerful counterfactual question. What if this specific piece of data was simply never included in the training set? How would the model's answer change? TDA is basically the ultimate causal intervention tool. We absolutely need it for auditing behavior, catching memorization, and debugging harmful outputs.
Which brings us to Part 2, the bottleneck of gradients and their compute constraints. Because if TDA is so incredibly important, why aren't we just using it everywhere, all the time? Well, the answer boils down to a massive compute bottleneck.
To really understand this bottleneck, we have to contrast the two main ways people attempt TDA. The absolute gold standard is called leave one out, or LOO, retraining. This literally means you train the model, take one single piece of data out, and train the entire model all over again from scratch just to see the difference. For large language models with billions of parameters, yeah, that is computationally impossible. You can't spend millions of dollars retraining a massive model just to test one single data point. Because of that, the industry has heavily relied on gradient methods like influence functions. These try to approximate the effect by looking at the model's parameters. But tracking gradients across billions of parameters is painfully expensive and eats up a ton of memory. Plus, these methods rely on local mathematical approximations that really struggle with the complex, non-convex landscapes of deep neural networks. In short, it's too slow, it's too expensive, and frankly, it's often inaccurate.
So, enter Part 3, Stride, a new approach. This is where our source material shifts the paradigm completely, and it is genuinely exciting stuff. So the crucial point is, the researchers behind Stride realized we need to totally stop looking at the massive parameter space.
Instead, they shift the focus entirely to the activation space. The activation space is the internal, low-dimensional functional representation of data happening within a neural network layer. It's much more lightweight. Stride completely bypasses the need to compute, store, or invert those massive parameter gradients because it models the functional effect of the training data right here, directly in the activation space.
Let's quickly walk through exactly how Stride pulls this off. It works in 3 structured phases. In phase 1, it learns lightweight steering operators offline. Instead of retraining the whole model, they trained it on randomly sampled subsets of data. These steering operators learn to mimic how the model would shift its behavior based on those data subsets, and they apply all of this to a frozen base model. Then, in phase 2, when you have a test query you want to investigate online, Stride generates a perturbation response vector. And finally, phase 3. It recovers the individual influences using something called sparse linear decomposition. Now, I know that sounds like a mouthful, but it's basically just working backward from those subset shifts to pinpoint the exact single piece of guilty data.
Moving into part 4, how sparse recovery works. We're going to explore the math magic here. And don't worry, I promise to make this accessible, so we'll look at the theory without getting bogged down in a whiteboard full of complex equations.
This concept is absolutely vital to understanding why Stride works. When you look at the distribution of influence scores across models, you see this immense concentration of influence mass resting on just a tiny fraction of the data. Think about it. When a model makes a specific prediction, it isn't relying evenly on its entire multi-terabyte database. Usually, only a minuscule fraction of the training examples actually influence that specific output. The vast majority of the training data has an influence score near 0 for that specific query. This sparsity, the fact that the influence is highly concentrated rather than uniformly spread out, is the foundational assumption that makes Stride's sparse recovery possible in the first place.
So how exactly does it find that tiny fraction of influential data? Well, Stride takes those subset-level measurements we talked about and applies compressive sensing. Think of compressive sensing kind of like trying to find a few guilty suspects hidden in a massive stadium crowd. You don't need to individually interrogate every single person if you can just ask the right group questions and use logic to deduce who is involved. By framing this as a sparse recovery problem and utilizing L1 minimization, which you might know as lasso, alongside subset measurements that act mathematically as expander graphs, Stride can uniquely and exactly pinpoint the individual data influences from highly compressed measurements. It's brilliant.
And the mathematical result of all this? 12. Stride is over 12 times faster than the strongest baseline gradient methods currently available, like log-raw and track. And the crazy part? Not only is it faster, but it also achieves state-of-the-art linear data modeling scores, or LDS, for large language model pre-training attribution. So it's significantly faster and more accurate, a real game changer.
Let's move to part 5, Stride in action. Let's look at the visual proof. We can see how this math translates into concrete visual evidence. The researchers tested Stride on image datasets, specifically CFR10, using a ResNet 9 architecture, so we can literally see what the AI considers influential.
Now, what's really interesting here is how cleanly Stride actually works. We take a held-out test image of a cat as our query. When we run it through Stride, we instantly see the 5 most positively influential training examples recovered from the massive training set. Notice how every single positive example directly supports the semantic class of the query. The AI used these specific images of cats sitting or laying down to successfully predict that our query image was, for sure, a cat.
But check this out. Stride doesn't just find the positive stuff. We can also see the most negative training examples for that exact same cat query. These are the examples that actively push the model away from guessing cat. And what are they? Dogs, deer, and a truck. These are competing or visually confusable classes. This proves that Stride isn't just doing some basic pixel matching search. It's capturing deep semantic alignment and understanding exactly what visual data opposes the correct prediction. We see the exact same consistency with a different test. Here, our query is an image of a ship. In the positively influential training examples it pulls up, they are reliably all other ships. The framework effectively and consistently retrieves the exact semantic class from the training corpus that supports the correct output. And when we check the negative training examples for that ship query, we see things like planes flying over water. It's a visually confusable concept, right? Blue backgrounds, similar geometric shapes, and these act in direct opposition during the model's prediction process. And this brilliantly illustrates a final qualitative sanity check. We query an image of a plane,
And Stride cleanly isolates positive support by pulling up 5 distinct, highly influential images of planes from the training data. The logic holds up perfectly across the board.
Wrapping up this visual evidence, the negative influences for the plane query include trucks, dogs, and ships. Stride absolutely succeeds in disentangling the complex web of AI memory, showing us the exact push and pull of the training data for every single prediction it makes.
Which brings us to part 6, the future of AI auditing and its real-world impact. So what is the so what of all this? Why does being able to trace an image of a cat or an AI's justification for lying actually matter to us?
Well, the authors sum it up perfectly in their conclusion. They say, ultimately, we hope this method serves as a foundational tool for scalable data curation, rigorous model auditing, and a deeper mechanistic understanding of how models learn from their training corpora. Stride's highly scalable activation space approach finally opens the door to truly transparent AI development. With this, we can actively audit models to see if they're memorizing copyrighted data. We could debug harmful outputs by finding exactly what bad data caused them in the first place, and we can curate vastly superior, safer datasets in the future.
Which leaves us with a pretty massive question. As transparent dataset auditing actually becomes a reality thanks to tools like Stride, how will mapping every single AI output back to its exact source data change our trust in these systems? When that black box is finally wide open, will we like what we see inside? Thank you so much for exploring the fascinating mechanics of AI memory with me today. Keep learning, stay curious, and I'll catch you on the next explainer.